When we look at data, we're looking for general trends. We're looking for something that would tell us about the data. And one of the most common themes is, where is the data centered on? When students are given a set of grades, they're always looking for the average because it gives them an indicator of how the class will perform on a particular test, or they will use their test score and compare it to the average to know where they fall. When companies use averages, they're using it as a measure of their performance as well, the general tendency of the revenue, say, or of sales or of profit. And that's where we get this concept of measure of central location, or a measure of central tendency. This concept helps us understand about the center of a particular variable. And some measures of central tendency include the mean, which is an average, the median, and the mode. And our analysis will also require descriptions of the data set, which can be done with percentiles and quartiles, because it's important to understand not only where the center of the data is, but how far it spreads from the mean. What are the endpoints? Is the distribution skewed to the right or skewed to the left? All of those different things are going to start with this concept of this central tendency. Now, the average, we kind of know, but we'll go through a little math formula here. The average or mean is the most commonly used measure of central tendency, and it's calculated by adding up all the values and dividing by the number of values in the data set. This gives an idea of the typical central value of the data itself. A sample mean, so if we had a sample, not an entire population, we're going to denote it by an X with a line over the top, and that's going to be pronounced X bar. I like to joke around that, on a Friday night, most statisticians like to hang around at X bar. But it's not a funny joke. Anyway, I digress. But here's the formula here for X bar. It is the sum of each individual observation. So that X with the little I, that I means each one. So I will go from, say, 1 to 50 if there are 50 observations. So it's X1 plus X2 plus X3 plus X4, each one of them. And we divide by N. Recall that N is the total number of observations. So it should be noted that while the sample mean is noted as X bar, the population mean, or estimated mean of the entire population, is noted by the Greek letter mu. That's the lowercase mu. When we refer to measures that come from a sample, we will use Latin letters such as X and S. We'll see the S shortly. When we're referring to population measures, we will use Greek letters such as mu, and that's the lowercase sigma. Now, to compute an average in Excel, we're going to use the average function because it will provide the average of the data set. The ... again refers to an entire column or an entire set of data within Excel. Again, we'll have a video specifically on using this. Now, the median of a variable in a data set is the center or middle. So median, you can think of a middle, use the same kind of alliteration there. Given a set of numbers, 1, 4, 5, 3, 4, 11, 4, 1, 2, the first thing to do is to order it. So we'll order that as 1, 1, 2, 3, 4, 4, 4, 5, 11. Since there are 9 numbers, the number in the middle is the 5th number, which in this case is the number 4. If there is an even number of numbers, simply take the average of the 2 middle numbers. So consider a slight variation here where we have 1, 1, 2, 3, 4, 5, 8, 9, 11, 12. What we'll end up doing is we'll end up taking the 2 middle numbers. The 2 middle numbers are 4 and 5. So therefore, the median is the average of these 2 numbers, which is 4.5. In Excel, they have a nice little function called median, and it provides the median of the data set, again, doing the same way. It does have some very good properties, especially when the data is not normally distributed. Normally distributed observations that we'll show later on, it's that bell curve. So if you're familiar with the bell curve, that's a normal distribution. But when the data doesn't follow a normal distribution or a bell curve, the median is actually more valuable than an average, and we'll see why later. The mode of a variable in a data set is the most frequent number appearing in the set. So given a set of numbers 1, 4, 5, 3, 4, 11, 4, 1, the most frequent here is 4. So the mode is 4. If 2 numbers appear most times in a set, such as 1, 4, 1, 3, 4, 11, 4, 1, there are two modes, 4 and 1, and this is called bimodal. If there are more than two modes, it's known as multimodal. This isn't very interesting, really, but the mode by itself is sometimes interesting, but anything higher than bimodal is not so interesting. In Excel, we do have a mode function, and it provides the mode of a data set. If you're using other applications like R or Python, the mode function is different. It is not mode. It is something totally different. In general, this is not very exciting, but it can provide some interesting insights into large data sets if there is mode or bimodal. Beyond that, like we said, it's not. Now, we're going to take a slightly different concept known as a geometric mean. The mean that we had shown before was the arithmetic mean. It is this x bar, which is the sum of each of the values divided by n. But the geometric mean, which we'll label as GM, is used when numbers are more exponentially related, such as financial measures, population growth, virus growth, or radioactive decay. In other words, if we have something that's linear like class grades, 88, 92, 91, and so forth, there's not really a relationship between them other than they're pretty much independent, and the only relationship is they occurred at the same time. But financial measures where the growth is compounded, in other words, a value tomorrow is related to the one today, but it was compounded because of the interest rates, or viruses that grow exponentially. So the virus amount here and the virus amount in 3 days, the virus amount in 5 days are all compounding because of the amount of virus that's out there. So the geometric mean can be interpreted as the average growth rate over a period of time and is more accurate and effective when there's a lot of volatility in a data set. When the data points are more independent and not skewed, the arithmetic mean is more accurate. This is what the geometric mean looks like, and this is about to scare about 85% of you who just saw that slide pop up. But let's not get too crazy here, because there's not that much that's going on. The geometric mean is obtained by taking the nth root. Now, the greatest thing about this is you don't have to calculate this by hand. All of our Excel functions and our calculators will do this. So let's just take this as what it is. Simply, what we're going to do is we're going to take each of the values and multiply them by each other. That's what that big Greek letter pi is. It stands for the product. And it says you're going to multiply every single one of the numbers together. So this part here that has this capital pi 1 to n xi just means take each individual observation. Again, n stands for the number of observations you have. So in this case, I is going to go from 1 to n. So we're going to take the first one, the second one, the third one, multiply them all. Then what we're going to do is we're going to take the nth root, where n is the number of items in your data set. In that case, we can actually do it two ways. If you're using a calculator, you probably have the x, the square root of x with the little n and the little v part of the square root, or you can just raise it to the power of 1 over n. Okay, it'll give you the same thing. In Excel, we can just use the geomean function, and it will give us the geometric mean of the data set. It will handle it for you automatically. Let's look at where this actually has value. Consider a data set with 7 annual returns for a given initial investment of $100. So recall that the geometric mean is the average growth, and since investments are compounded, the growth rate is what an investor would be interested in. In the example to the right, the arithmetic and geometric means of the percent return are computed. So in year 1, we would get $105. In year 2, we would get $116. Year 3, we're getting $124. We're looking at all the amounts and we're computing the returns. Our returns correspond to 5%, 10%, 7%, 12%, 13, 2, and 4. So if you took the arithmetic mean of the returns, you would get 8.5%. But if you take the geometric mean, you get 8.05%. Which is a more accurate measure because of the volatility in the returns. So this is an example showing you where the difference is between that arithmetic mean and the geometric mean. And it has to do with if there is any compounding or exponential growth, that's when you're using that geometric mean. If you don't see that, then you're using an arithmetic mean. And this difference is critical because, again, a percent return of 8.5% after 7 years would be $181. but a percent return of 8.05 is $175. So if an investor was told that the rate would be 8.5 based on the arithmetic mean, the value would be much higher than the effective return. And so they might be upset because that return didn't happen that way. The geometric mean will provide a better estimate of the expected return.